Hello everyone, I'm Zoi Kaoudi from TU Berlin, and I will talk about training data generation for ML-based query optimization. In Agora, an open data ecosystem we're building, users not only contribute datasets, algorithms, and systems, but can also ask the ecosystem to execute a task for them. In this case, the execution layer of Agora is possible to determine where to execute this task, meaning in which system or even in which location. And for that, some query optimization is required. Now, we know from previous that there are a lot of problems with the traditional cost-based optimization in such settings, such as it's very hard to fine-tune all the hyperparameters for all the cost formulas, or that these formulas assume linear functions which do not really depict reality. So for that, machine learning comes to the rescue. So by replacing the cost model with a machine learning model, there is no need of a linear assumption anymore. We don't have to manually tune any cost formulas, and we still achieve good performance by choosing good plans. However, we know that machine learning models are data hungry, so we need a lot of training data. So a naive solution to generate such training data is to manually create thousands of plans, so both good and bad plans, extract the features for each of the plan, and then execute all the plans to collect their labels, which means their execution runtime. However, this is very tedious and time-consuming, and let me show you why it's time-consuming. Here you can see the time that it required us to collect the runtime of a different number of jobs on just 1 gigabyte of data, and to collect the labels for 10,000 queries, it would require a bit more than 4 days. Now, if we extrapolate that to 1 terabyte of data, that would take us more than 6 months. So for that, what we propose is, instead of manually creating plans, we synthetically generate plans based on an initial small workload that the user has in mind. We extract similarly the features for each plan, and now instead of executing all the plans, we execute just a small sample of them and forecast the rest. For that, we have built data farm, which consists of 3 main steps. In the first step of plan generation, we output abstract plans. In the second step, we instantiate these abstract plans with the join predicates and selection predicates based on the input data. And in the third step, we generate the labels. So we collect the runtimes of these synthetically generated plans. For that, we sample some of them, execute them, and get the real runtime. We create a machine learning model, which is then used to forecast the runtime of the rest query plans. Now, if we are satisfied with the results, so if our prediction quality is good, we just output the training data. If not, we go back and sample more jobs and execute them, build another machine learning model, and so on until we get a satisfactory training data set. To further enhance the process of labeling, we have decided to include the human in the loop, who has insights on which jobs actually would be useful to execute and which not. And this is done via a very insightful and intuitive user interface where he can profile different jobs and compare them. Thank you very much.
Hi, I'm Robin from the Hasso Plattner Institute, and I will give you a short demonstration.
Welcome to GUI Data Farm, farming your ML-based query optimizers food. We guide users through the process of generating custom workloads for a query optimizer. The system is fully implemented. It consists of 3 main components: the abstract plan generator, synthetic job instantiator, and the label forecaster. We're going to show you how it works. Let's start by uploading the execution plans of your existing Dataflow jobs. GUI Data Farm analyzes the input workload and provides various statistics. Here we see the operating characteristics, and here we see the learned transition matrices. These show the transitions as learned by the system. The first visualization shows all jobs as bubbles, representing the operators of each job. So say we want to exclude all the jobs with the bulk iteration, we just deselect the bubbles and upload the workload profile. Now we see the system has updated the workload profile and there is no bulk iteration operator anymore. Now that we've uploaded and customized our input workload, we turn to the abstract plan generator. This will take all the data from the input workload and generate abstract plans. So here we can change the amount of abstract plans, the maximum operators in the abstract plans, and the maximum join operators in the plans. After letting the system generate these plans with our custom settings, we turn to the synthetic job instantiator. We can then select or deselect abstract plans if we want them for a desired workload that we generate. We can even inspect them one by one. Now the user specifies how many diverse instances he wants to generate per plan to begin the instantiation process. We also provide a metadata file containing information about the tables and the input data. Then we choose a target platform like Flink, Spark, or Storm. The system will now start generating these instantiated jobs. When the jobs have been instantiated, we see an overview of the statistics of the generated jobs. So we generated 100 jobs with an average of 10 operators per job and 346,000 in terms of output cardinality. Then we can compare the operator frequency of the original and generated workload. We can also see the distribution of the input-output cardinalities. This demonstrates that the generated jobs cover most of the user input data domain. At this point, if we only need a benchmark for our data management systems, we can stop here downloading the set of generated jobs. If instead we need label jobs, for instance for an ML-based query optimizer, then we can proceed to the label forecaster. First we select the target label execution time. Then we select our initial job sampler. Then we adjust the number of initial jobs that we execute, the uncertainty threshold for early stopping, the max iterations, and the max time budget. Then we arrive at the active learning controller. This user interface is designed to let the human get the best out of the generated data. The top shows the main information characteristics, along with the job execution state. Then we expand the first collapsible section. This contains performance characteristics of the models trained on our currently executed jobs. The job feature overview includes an interactive adjustable graph with all jobs and the ability to select the feature plotted from a drop-down list. We can also make a decision on the basis of uncertainty qualities for each job. With the instantiated job characteristics, we can select just those jobs that use the right tables and have the right amount of operators. We are also able to compare our generated workload to the original workload in this interface. The model explanation analysis shows the importance of each feature in the model. Then, with the buttons below, we can either choose to execute the selected jobs and go to the next iteration of our process, or download the workload at this point. We also provide an information-rich interface for each individual job. We now click on job 9v1, which still has to be executed. On the top we see information characteristics about this job. Then we show the instantiated plan characteristics, which displays the abstract plan and detailed instantiation characteristics, which the user can compare to the desired workload. The feature overview shows the feature values of the job compared to the general characteristics for the complete job set. We also have a similar jobs interface, which shows executed jobs similar in operator length, cardinalities, and data sources. This overview helps the user with job selection. The last element of the job explorer is the prediction analysis. It shows the explainability for the predicted label with respect to the job features. With the button below, we can choose to execute this job. From just a few jobs, using our systems, we generate numerous jobs. Then our system can help us select just those jobs we want. After this, we get a custom but varied workload. Now we show an example use of our system. So first we look at the model explanation analysis, and we see that the out-cardinality standard deviation is quite an important feature for using our workload as training data. We then look at the value of the original jobs for the feature. In this case, we want to make a model that performs well on the original workload. To do this, we go to the job feature overview and select the out-cardinality standard deviation. Then we can just select the dots that are close to the value we want, and this will execute the jobs and include them in our final workload. Finally, we navigate to the bottom of the active learning controller and go to the next generation with a push of a button. Using steps like these, we are able to decrease the root mean squared error by over 21% over selecting the whole workload.
To be more specific, let's go to the experimental evaluation. We also analyzed the performance of GUI data farm. For this, we generated 4 large heterogeneous datasets. We introduced them as W1 to W4. In the interest of time, we will only show W1 and W3, which are the most heterogeneous amongst each other. Let's look at the experimental setup. We start from a small set of jobs and generate a bigger set of jobs, which are called, as seen in the previous slides, W1 to W4. This is to compare GUI data farm with other approaches. From this, we use different sampling techniques to sample 500 jobs. Then we execute this subset and thereby give them a label. With this subset, we train a model called the sampled model. We then use this model to label the bigger set that we extracted the 500 jobs from. Using this fully labeled workload, we then train another model called the complete model. Using this model, we label the original jobs and compare the labels to the ground truth. So now let's find out how does GUI data farm perform with respect to other methods. We compared 4 different job selection techniques. These different job selection techniques are executing a random sample, completely executing all jobs, executing data farm but without the human, and executing data farm with the human. We used the gradient boosting random forest regressor from the XGBoost library. We compared performance with several often used metrics. Here I'll be showing you the R-squared value. Let's look at the results. Here we see that GUI data farm outperforms all other methods for both workloads. Specifically, it outperforms data farm without the human with a significant margin. It is particular that also the completely executed set is outperformed. This is probably due to overfitting and the inclusion of jobs that reduced prediction accuracy. We did another experiment that compares the execution time of the different job selection techniques. So we compare the execution time of each technique, and the job selection techniques are taken from the previous experiment. So what are the results? In these results, we see that using GUI data farm takes significantly less time than executing the complete workload. We also see that the execution time of GUI data farm is similar to the other techniques while improving the performance significantly. With GUI data farm, we are bringing human power to data generation. Using these two QR codes, you can check out the code on GitHub and you can watch the demo video. I have been Robin and I've been presenting with Zoi. If you have any questions or suggestions, do not hesitate to contact us. Thank you very much.